We measure a lot of things in science, and in order to measure something, we need units. And I cannot emphasize enough how important units are. Units are critical. And here's an example from real life. Back in 1999, NASA lost the Mars Climate Orbiter, $125 million. It went out to orbit around Mars, and the calculations weren't right. And so it descended into too low of an orbit, got caught by the gravity, and crashed, burned up, gone. How does this happen? So they investigated. The root cause was a failed translation of English units into metric units. Centimeters versus inches. They got it up there, they realized they needed to adjust the trajectory. The software in the computers, I believe, was using metric units. They did the calculations in English units and punched the numbers into the computer. That doesn't work because inches are different than centimeters. So we're not going to be like NASA. We're not going to screw up because of our units. Units are very, very important. There are two common systems, the metric system and the English system. Metric system is what's used by most of the world, and here in the United States we just have to be ornery, and we are clinging to our English system. Scientists use the metric system. Okay? So if you're in doubt in lab whether you should measure something in centimeters or inches, choose centimeters. Technically, we use what's called the International System of Units, or the SI system. That, in my opinion, is the same as the metric system. The distinctions are so minute that it just doesn't matter, not worth talking about. So I use SI system, metric system interchangeably. These are the base units in the SI system. For length, the meter; for mass, the kilogram; time is the second, and it's the same as the second that we use. Temperature is a Kelvin. The amount of substance is measured in moles, electric current in amperes, and luminous intensity in candelas. Now those last two we're not going to get into in this class, but they are base units in the SI system. It is important to have a rough idea of how long these units are. So a meter is slightly longer than a yard. I'm not sure why this is down here on the floor, but so is this a meter stick or a yardstick? It's chemistry lab. What do you think? It's a meter stick, and I'm moving it around so you can't tell. So on this side, there are 100 centimeters. This is a meter. On the other side, it's marked in inches, but it goes up not to 36 inches, but to about 39 and a half inches. But a meter and a yard are roughly the same size. So kind of stick that in your brain. All of these things are defined very, very specifically, and I've put that up there and it's in your book, but I'm not going to test you on that. A kilogram. The mass of an object is the quantity of matter. Mass and weight are not exactly the same. The weight of an object has to do with the force of gravity pulling on it. The mass is the amount of matter. So if you take an object and you weigh it on Earth and you take it to the moon and you weigh it there, the weight is different because the force of gravity is different on the moon. But the mass is the same. Okay? We typically use mass and weight interchangeably because if we're going to stay on the planet, they're basically the same. They're not going to change. So the SI system is a kilogram. We use kilograms in science, but it's an awfully large unit. A kilogram is just over 2 pounds. So, think about that, like a 2-pound bag of flour or something, that's a kilogram. In chemistry lab, we typically use a gram. It's a smaller unit, it's more appropriate. It's 1/1000th of a kilogram. A nickel is 5 cents. A nickel weighs 5 grams. So that'll give you an idea. A gram is a small amount of matter. Time, the duration of an event, a second, and of course that is the same as we use in everyday life. It's just got a crazy definition there. Kelvin is the unit of temperature. I mentioned this earlier. Temperature is related to thermal energy, a form of kinetic energy. So temperature measures the average kinetic energy of the particles in that sample. Temperature also determines thermal energy transfer, which direction it will go. It always goes from the warmer to the colder. There are 3 temperature scales in common use. The Fahrenheit scale, which is what the weatherman reports the weather in, the Celsius scale, and the Kelvin scale. The Fahrenheit scale was the original one, and then it's got some funny units in it. Funny numbers. So 32 degrees and 212 degrees, right? So that's an English system unit. The metric system units are based on powers of 10, and so Celsius is a metric unit. Here we have water freezing at 0 instead of 32, and water boiling at 100. And those numbers were chosen to be nice round numbers, powers of 10. So we've got 0 and 100. So between the Fahrenheit and the Celsius, we have 2 things that are different. The 0 point is different, and the size of the divisions is different. Here we have 180 degrees, here we have 100 degrees. Then over here we have the Kelvin temperature scale, which we will be using especially when we talk about gases. This has 100 divisions, so 100 kelvins is the same as 100 degrees Celsius, but 0's in a different place. The Kelvin scale is based on the concept of absolute 0, the lowest possible temperature at which all motion would cease. And so on the Kelvin scale, you do not ever have a negative number, and that's a big advantage of the Kelvin scale. We need to be able to convert between Fahrenheit and Celsius. And so here are the 2 equations, and you should memorize these. The Kelvin one's pretty easy. The Celsius one takes a little more thinking, but you can do it. These conversions have to be done with formulas because of the relationships. The zeros are not in the same place. When we convert inches to centimeters, a distance of 0 is 0 in any unit. But on a temperature scale, 0 is not the same. And so we have to use these equations. So let's do an example. Gallium is a solid metal at room temperature, but will melt to a liquid in your hand. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on? A, the Celsius scale, and B, the Kelvin scale. So we're asked to convert degrees Fahrenheit into Celsius and into Kelvin. Celsius and Fahrenheit. Celsius and Kelvin. Summer break was not long enough. So let's look at A first. We've got Fahrenheit, we want Celsius. We need the equation. So here's the equation. Degrees Celsius is Fahrenheit minus 32 divided by 1.8. There we go. Okay, I'm having technical difficulties. There we go. Okay. So degrees Celsius is equal to the Fahrenheit temperature minus 32, that whole quantity divided by 1.8. So we'll take that temperature, 85.6, subtract 32, and divide by 1.8. It is important that you communicate correctly to your calculator that you want to subtract those numbers and take the result of that and divide by 1.8. So if you have your calculator, get it out and make sure that your calculator is listening to you. 85.6 minus 32. Personally, I don't like using parentheses. You can use the parentheses, or what I do is 85.6 minus 32, and I press enter to make it finish the subtraction, and then I divide by 1.8. And I'm going to round this to the same decimal place as the original value. We'll talk more about that later. My calculator is telling me 29.77 repeating. I'm going to round that to 29.8 degrees Celsius. Any questions? Then there's a part B. Convert that temperature to Kelvin. There was not an equation for Fahrenheit to Kelvin. You have to convert the Fahrenheit into Celsius and then the Celsius into Kelvin. So here we've got the Celsius temperature. So the Kelvin temperature equals the Celsius temperature plus 273.15. I'm going to use the unrounded number here. We won't get hung up on that just yet. Plus 273.15. I still have that number in my calculator. I'm just going to add 273.15. This gives me 302.927 repeating. I'm also going to round this to the same decimal place as the original number, to the tenths. And so that's going to give me 302.9. And the unit is capital K, no degree sign. Any questions? So the metric system is based on powers of 10. The thing about units is you can't just have one unit for length, right? Because if you want to measure how wide your piece of paper is, you'd want to use inches. If you want to measure the distance between Fresno and San Francisco, you don't want to use inches, do you? The number would be too big. You want to use a larger unit. So we need units that have different sizes. In the metric system, we use prefixes to change the size of the units. The concept of scientific notation is very, very important. We're going to use scientific notation a lot. I'm going to assume that you already know scientific notation. I know that some of you are rusty on that. There's an appendix in your textbook. Go check that out, and if you need help, come talk to me. I'm not going to do it in lecture. So the multipliers in the metric system change the size by powers of 10, like the exponent in scientific notation. So as an example, this unit, kilometer. Meter is the base unit, kilo is a prefix. The prefix kilo means 1,000 or 10 to the 3. So when I put kilo in front of meter, I multiply the size of the meter by that factor. So 1 kilometer is equal to 1,000 meters or 10 to the 3rd meters. Okay? So these are a lot of the metric prefixes. There are more, but these are the most important ones, the most common ones. And there are many situations in life where it would be great if you could do all the things, but there just isn't time to do everything, right? And so you kind of have to cut your losses, pick and choose, do the most important things. So I'm just going to show you the most important ones here. Centi is important, milli, micro, kilo. Those are probably the most important ones. And after that would be mega and nano. So if you can't manage all of them, at least get the ones with arrows. These prefixes and their multipliers are going to be on the memorization quiz that will be given next week. So what you need to learn is the name of the prefix, its symbol, and the multiplier. Now this is all very nice and everything, but those zeros are just way too hard to count. You learn this, the power of 10, 10 to the what? And if you look at this, most of the exponents here are factors of 3. So here we have 10 to the third, 10 to the 6th, 10 to the 9, 10 to the 12, etc. It's just these guys in the middle that are a little bit off. Here's minus 3, minus 6, minus 9. So let's look at some examples. So how long is 4.5 megameters in meters? What does the prefix mega mean? 10 to the 6, right? So 4.5 megameters. What I'm going to do there is, instead of writing capital M, I'm going to write what it means. 4.5 10 to the 6 meters. Well, let's put a little multiplication sign in there, and I've done that conversion, and now I have the relationship 4.5 times 10 to the 6 meters is equal to 4.5 megameters. So these prefixes are shorthand, a nickname for this larger thing. 7.13 times 10 to the minus 9 liters is equivalent to how many nanoliters? Well, what does nano mean? 10 to the 9. So you can look it up. Nano means 10 to the minus 9. It's a multiplier. So 7.1, that's just not a very good one, 7.13 times 10 to the minus 9 liters. Instead of times 10 to the minus 9, I'm going to write the abbreviation for it. 7.13 nanoliters. The nano changes the size of the unit, making it more appropriate for what's being measured here, so that we get more reasonable numbers. Any questions? So we talked about base units. There's also derived units. These are units that are a combination of other units. And the ones that are most important to us are volume and density. So volume is a measure of space, a measure of volume, right? It's hard to define volume without using the word volume. If you take a unit of length and cube it, multiply it by itself twice, you get a unit of volume. And that comes from, geometry, where if you have a cube, how do you find the volume of the cube? Well, the volume of the cube is equal to the length times the width times the height. If you measure each of those in centimeters, then the unit of volume ends up being centimeters cubed, right? So a unit of length cubed is a unit of volume. That's a derived unit because it's derived from units of length. Other volume units are liters and milliliters. So milli means 10 to the minus 3. A milliliter is 1/1000th of a liter. We typically use those for measuring volumes of liquids, whereas we use things like millimeters cubed for solids. So here we have a big cube that's 10 centimeters on a side. Right? So there's 10 little centimeter blocks here in each direction. So we could figure out how many small cubes are needed to compose the large cube. So you could take that apart and count them, but that would be tedious. So here we have this little cube that's 1 centimeter on a side. So the volume of that would be 1 cubic centimeter. The volume of this whole thing would be 10 centimeters times 10 centimeters times 10 centimeters. So that would be 1,000 cubic centimeters. it would take 1,000 of these little boxes to make the big box. Does that make sense? This little one has a volume of 1 cubic centimeter. 1 cubic centimeter, that unit has another name. It's also called a milliliter. In medicine, they call it a cc. cc for cubic centimeter. So if this is a milliliter, then this whole thing is 1,000 milliliters. Right? So 1,000 cubic centimeters is the same as 1,000 milliliters. Milli means what? 10 to the negative 3. So if I have 1,000 is 10 to the third, right? So 10 to the third milliliters, 10 to the third times 10 to the minus third liters, that's 1 liter. A milliliter is 1/1000th of a liter. Most important thing to get from this is a cubic centimeter is the same as a milliliter. Any questions? That's a cubic meter. I had a chance to go to Norway last fall and went to the Norwegian Museum of Science and Technology, and they had a really cool display on units. And so this is a glass box that's 1 meter on a side, and it's open on one side so that you could sit in it. And so that's how big a meter cubed is. That's a big thing, you know. You would sit in there quite comfortably. So these are some common units and their equivalents. What do you need to memorize? Well, you need to memorize this one. A cubic centimeter is equal to a milliliter. And I want you to remember this one. 1 inch is exactly 2.54 centimeters. We use those a lot. A lot of these other things are relating miles to kilometers, English units, and metric units. I don't expect you to memorize those. This is the only one, okay? If you need those on an exam, I'll give them to you. You may need them in a homework assignment. Look them up. I don't recommend asking Siri to convert the units for you because you won't be able to use her on the exam. So look at a table like this, just a simple one, so that you get the practice in converting the units. So what about density? Density is the ratio of mass to volume. Density is a physical property of a substance. The density of something does not change when you change its size. If I take this meter stick, it has a certain volume and a certain mass. It has a density. If I cut the meter stick in half and look at 1/2 of the meter stick, does the density change? No, because I cut the mass in half and I cut the volume in half. And so the relationship, the ratio remains the same. Doesn't matter if it's big or small. It's a physical property, an intrinsic property of the substance. So density is mass divided by volume. That's a relationship you should memorize. Density is mass over volume. Common units, grams per milliliter, grams per cubic centimeter. Density does change somewhat with temperature. Not because the mass changes, but because volume is somewhat temperature dependent. A lot of things, when you heat them, they will expand a little bit. And so density does change slightly with temperature. That's why when you look at a table like this, it'll give the density of some common substances and it'll specify a temperature. Because if you're going to do this at, say, 95 degrees Celsius, some of these densities would be different. So densities like this, again, we're not going to memorize those except for water. Liquid water unless you're given a more precise density, liquid water has a density of 1 gram per milliliter. So here we see some things that are less dense than water and some things that are more dense than water. This is a section that will never end. Intensive and extensive properties. So we talked about chemical and physical properties. Here's another way to define properties. An intensive property does not depend on the amount of substance. So density is an intensive property. You could think intrinsic. It doesn't matter if you cut the thing in half. The density stays the same. Other examples would be melting point or color. If you take a block of ice and you cut it in half, does the melting point of the ice change? Nope. If I cut this meter stick in half, does its color change? No. Doesn't matter how much of it there is. That's an intensive property. An extensive property, think external, does depend on the amount of substance. So examples there would be mass, length, volume. I cut the meter stick in half, it's no longer 1 meter in length. It's changed. Its length is now half a meter. Its volume has changed. Its mass has changed. So those are extensive properties. Intensive properties can be used to identify substances. You've got 2 different metals. They may look very similar. You're trying to figure out, is this lead? Is it titanium? We're not sure. You can measure the melting point, and that will tell you the difference. You can measure the density. So intensive properties can be used to identify substances. I'm going to stop here, and we'll pick this up on Wednesday.